Today, we're diving into a strategy so powerful, so fundamental, that it's basically the backbone of modern computing. It's an ancient idea, really, but it's come to rule a digital kingdom. Let's see how it works. All right, let's play a game. Imagine you're a king. You've got a million subjects all standing in one massive, disorganized line. Your job? Arrange every single one of them by height. Where would you even start? A million people. That's a truly mind-boggling task. Well, if you tried this simple, obvious approach, it would be a complete and utter catastrophe. Taking the first person, comparing them to everyone else, then the second person, comparing them to everyone else. For a million subjects, you'd be looking at nearly 2 quadrillion steps. That's an insane number. Your kingdom would just grind to a halt. That brute force method, it just doesn't work when things get big. But then, just when you're about to give up, a wise advisor steps forward with a piece of timeless wisdom. They tell you, don't try to solve this giant problem all at once. That's madness. Instead, they say, break it into smaller, manageable pieces. Solve those little pieces, and then put the solutions back together. Now that sounds promising. This brilliant idea actually has a name in computer science: divide and conquer. It's this powerful way of thinking where you recursively break a problem down. And recursively just means you apply the same logic over and over again until the pieces are so small they're laughably easy to solve. Then you just weave those simple solutions back together. So the king loves this idea. He immediately issues a royal decree, a simple but brilliant 3-step plan for the entire kingdom to follow. And here's the decree. It's just 3 steps. First, divide. You split that massive line of people into smaller groups. Second, conquer. You solve the problem for those small groups. The key here is you need a stopping point, what programmers call a base case. For us, that's when you have a group with just one person. A group of 1 is already sorted, right? And finally, step 3, combine. You merge those sorted groups back together. Divide, conquer, combine. That's the mantra. Okay, enough with the theory. Let's see this royal decree in action. We're going to use a classic algorithm that is the perfect example of this strategy. It's called merge sort. It's time to bring some order to this chaos. So instead of tackling a million subjects right away, we'll start with just one small, disorganized province. We've got 8 subjects here, represented by these numbers. As you can see, they're all over the place. Our goal is to get them sorted from smallest to largest. First move, we follow the decree. Step 1, divide. And we do just that. Boom! We split the line right down the middle. Now, instead of one messy group of 8, we have 2 slightly less messy groups of 4. But we don't stop there. This is the recursive part, remember? We apply the exact same logic again. We take those 2 groups and split them in half. So now we've got 4 even smaller groups to worry about. And we keep on dividing until we literally can't divide anymore. We're left with these tiny provinces of just 1 subject each. And this is our base case. A group of 1 is, by definition, already sorted. So the conquer step is done. All the tiny problems have been solved. Now for the magic. Step 3, combine. We start working our way back up by merging these tiny sorted provinces. So we take the 5 and the 2. We compare them. Which is smaller? The 2. So it goes first in our new list, then the 5. So 5 and 2 become the sorted group 2, 5. See? We just repeat that simple comparison for every pair, and we just keep that process rolling. We take our new, larger sorted groups, like 2, 5 and 4, 7, and we merge them using the exact same logic. We're just comparing the first items in each list, picking the smaller one, and building a new, even larger sorted list, one step at a time. This leaves us with 2 perfectly sorted halves. And finally, we do one last merge on the 2 remaining halves. And just like that, through this systematic process of breaking things down and building them back up, our entire province is in perfect order. This strategy was a massive success. So why is this so much better? Why go through all that trouble? Well, this table says it all. As our number of items, n, gets bigger, look at what happens. The brute force method, n squared, just explodes. The work grows exponentially. But our smart divide and conquer approach, what we call n log n, it grows so much more slowly. One method becomes impossible, while the other stays totally efficient. And this brings us to what might be the most important lesson here. A better algorithm is way more important than faster hardware. Get this. Let's imagine a super fast computer, computer A, running that slow brute force algorithm. And we'll pit it against computer B, a machine that's 100 times slower, but it's running our smart divide and conquer algorithm. Who wins? It's not even close. The slower computer with the smarter algorithm sorts 1,000,000 items in about 20 minutes. The supercomputer? It's still chugging away for over 5.5 hours. That's the power of a good algorithm.
Now, for anyone who loves the math behind it all, this is how we can actually prove it. This formula is called a recurrence relation. It's really just a fancy way of saying that the time to solve the whole problem is equal to the time it takes to divide it up, plus the time it takes to solve all the little pieces. We don't need to get lost in the weeds here, but this is the mathematical signature that lets us prove how incredibly efficient this strategy really is.
But the influence of this one idea goes so far beyond just sorting a line of people. This single strategy has built an entire empire of powerful and efficient algorithms that run our world. So many of the most famous algorithms you hear about are built on this exact foundation. You've got quicksort, another super fast sorting method. You have binary search, the crazy fast way to find something in a sorted list by just cutting the search area in half over and over. A classic divide and conquer move. Even super advanced stuff for graphics and data science, they all owe their power to this simple, elegant idea. You see, in the end, divide and conquer isn't just a technique for writing code. It's a fundamental way to approach problems. It doesn't matter if you're managing a huge project, learning a difficult new skill, or, organizing a kingdom. The principle is exactly the same. Take that scary, massive challenge, break it down into pieces you can actually solve, conquer them one by one, and then combine your small victories into one big solution. So the only question left is, what problem are you going to conquer with?